Okay, so here we are with our next titration that we're going over, and unlike the one we previously done, this is going to be a weak acid strong base. So I know you may be jumping in on this video and not the other. We previously have just completed the titration curve for a strong acid and strong base, and so what we're going to find is in these two curves that I'm trying to show and teach you is that I was using the same concentration of both acids, and by these two printed graphs from this titration we're going to be able to learn something in the differences in the calculation. So we spent a lot of time with the strong acid strong base titration with doing just complete stoichiometry, completion reaction, and certainly in all titrations there's a completion reaction, but we're going to see now equilibrium creep up here. All right, so let's spend some time on a weak acid, weak base, and talk about our 5 points. I'm always talking about 5 points that you have to be able to either calculate and create a curve, or in my case, what I'm going to do is take a curve and I'm going to try to, from the experimental evidence, using a pH probe and measuring the pH changes over time in this case, and it's really volume of the base added. What I'm going to show you is these 5 points. If you calculate them and learn how to either predict them or validate them on this curve, those are all the calculations you need to do with any single advanced placement chemistry problem. So let's be crazy and get started. All right, so what I'm going to do here is I'm going to go talk about the same 5 points, broken record. But these, like I said, are going to have some equilibrium issues that we didn't have. So first and foremost, let's talk about the reaction. We're having acetic acid, okay, the acetate ion H, plus a strong base. So let's talk about the fact that although equilibrium is going to creep in here, we're still talking about titration. This is a driven reaction, and we need a strong base to drive a weak acid, okay, so that it completely dissociates. All right, so this is part of the net ion equation. So let's start with the net ion equation. So we're going to have hydrogen, okay, and we're going to have the acetate C2H3O2, okay. And then we're going to have our hydroxide. And of course, we're delivering the hydroxide by sodium hydroxide, but that's completely soluble, and the sodium doesn't ionize water. It's a big ion, and it has a low charge density, as we've talked about. And in any case, we get rid of the sodium. It's a spectator, and so what's going to happen is this hydroxide is going to pull a hydrogen off the acetic acid, which we know is vinegar. In West Hampton we say vinagre, it's kind of a weird thing. But in any case, we pull the H away and we're going to make water. All right, but what's remaining, unlike the strong acid, strong base, is we're going to have a conjugate base, okay, that can ionize water. And that's going to show its ugly head a little bit in different parts of these points that we go over. So we should know that this is the conjugate acid. It's the acetic acid, it's a weak acid, and this is the conjugate base. Now I know I went over the strong acid, strong base, and over the 5 basic points there, no pun intended, but it's important to realize that this kind of titration here is the norm. Strong acid, strong base is not normally the norm. I hate to say that twice, but I did. And the reason is that most acid and bases are weak. And to find some information about a weak acid or a weak base, we use a strong base or a strong acid to drive the reaction forward. So in this case, we're talking about a weak acid, vinegar or vinagre, and we're going to drive it forward by the strong base helping it give off each H+. So as many C2H3O2s out there, we need that many hydroxides to pull each hydroxide off. We're going to make this weak acid feel like a strong acid in terms of pulling it forward. And we'll talk about that. It's a stoichiometric event. All right. So this is the net ion equation. Notice we do not have H plus hydroxide equal water. It's only for strong acid and strong base. Okay. So let's talk about the points that you have to know as I've done before. This is point 1. Okay, this equivalence point, which is somewhere in the middle here, is going to be, well, the half equivalence will be 2, there's going to be a 3, so this will be 4, and this will be 5. Now I'm skipping because there is a half equivalence here somewhere. I'm just going to kind of mark it here. That's going to be 2. And in number 3, I'm going to write with a different pen to show that 3 really could be any position above the 0 volume of base added in this case till just below. So 3 could be anywhere here. I'll just write it that way. So when I'm writing the third point, that's going to be some position in this titration curve that's above 0 volume of base added or titrant added, but somewhere below the equivalence point. It could be anywhere here. Now I'm going to put it here, but I can answer that position. So the points that I have here, the 5 points, if you can understand how to calculate and predict, or in this case, what we're going to do is take this curve and validate and see how well our data really matches the known values, we understand all of the calculations, okay, that we need to do in any type of AP chemistry problem. So let's be crazy and start. So the first thing is to, as for me, I'm going to go find that equivalence point. That by far is the most important. So number 4 is the equivalence point. Okay, and you should be understand that this is the most important of them all. It's our jumping off point. And what's so important about the equivalence point is stoichiometrically, remember, titrations are stoichiometric driven events. At this position, at this point, which is somewhere in the middle of the asymptote, the H plus, the protons that were on our weak acid, okay, equal the amount of hydroxides added. That means at this point in time, okay, we have added just enough base to completely neutralize this weak acid. Okay, now if you don't understand what's going on here, what we're doing is we're taking a base that's in a burette. Now, of course, we can have this written the other way. We could be doing dropping an acid on a weak base, but in this case, you can see the pH going up, we're adding a base. And so to visualize, we have a burette here, dropping hydroxides. And important, at this position right here, we've got ourselves a beaker. And that beaker, all right, has 25 milliliters of acid in it, okay? And it's 25 milliliters. I'm giving you that right here, okay? So we're starting with 25 milliliters of acetic acid. We do not know its concentration. We're dropping hydroxide, and we know that the hydroxide concentration is 0.1 molar. So the question is, how much base do I have to add to this acid so that we've completely wiped away all of the protons available from the weak acid? And that's that point there. And that's a stoichiometric event. It takes 1 hydroxide per one of these. Now we know that this acid is not good at giving off its protons, but party people, this base forces it, makes it feel like that. It's going to drive it. Normally this acid would stay around this pH for that certain concentration, but we're going to force it to do all these other things, force it to give up its H+. Okay, so let's get started. So we're going to start with trying to find the molarity of this acid sitting in this position on number 1. So we're kind of using point number 4 and point number 1 collectively to answer that question. All right, so we're kind of doing that. So we're going to start with point number 4 because it's a jumping off point, and we're going to use that. Now the question is, how do I start? Well, now that I have what I think visibly, and by the way, I'm looking at my asymptote and trying to find a value in between, and maybe it's a little bit higher, maybe it's right here, who knows. The bottom line is, I'm going to take that value and go all the way down. Now, normally these titration curves, this is volume of base added, and that's true, except when I did this video, okay, when I ran this titration, okay, what I did was I basically have a flow rate. So if I play this, okay, at some point, or if we paid our Wi-Fi bill, okay, what I'm doing is turning on the opening up the burette. I figured out how many milliliters per second, and so if you notice in this titration, okay, we're starting to go up as we start. Now, I'm going to stop this here. Okay, and I don't want to see me there. Now what I want to talk about is at this position here, the pH is sitting in a beaker. If I said to you, hey, what is the concentration of acid that we started with? All right, well, we had to add a certain amount of base. Now, this video is based upon, because I couldn't measure the volume, I didn't use a drip counter, I used time. And what I know is that there's 1 milliliter per every 2.8 seconds. So normally this would be reading the volume on the bottom. In any case, let's just go with the data that I have here. So I have 1 milliliter per 2.8 seconds. So right here it says, it's hard to read, but if you download this sheet, you could do this with me either on my video or from this video, look under the details, and you could get this same hard copy. But I get about 39, okay? Now, if you get 39, for me, I'm just gonna do 39, and this is seconds, and I'm gonna get rid of seconds, and I know that there's 2.8 seconds for every 1 milliliter. All right, so when I take my 39 seconds divided by 2.8, I get approximately 14 milliliters, okay? So I'm gonna say that this point right here is 14. And again, I'm approximating a little bit, and I can do that because it's my video. All right, so this is 14 milliliters. That's important, okay? Most of the time, you will not have to do this calculation, okay? It's just how I did it. All right, so 14 milliliters. And I guess we could have treated the time as milliliters here and moved on, but hey, I'm tall. Now, so we got 14 mils, my equivalence point. That's important. That's a great leading off point. That means it took 14 milliliters of a what? 0.1 molar solution to do what? To neutralize my H+. So what I'm going to find here is moles. Got to go to moles. How many hydroxides did it take in my burette to actually match 1-to-1 with my acetic acid? So here's what I do. Okay, and it's something we're going to do a lot of. We're going to solve for the moles. Okay, so if you notice, I have a 0.1 molar solution, 0.10 molar. And what am I going to do with that? Molarity times volume in liters gives me moles, because molarity is mole over liter times liter. It would cancel. Remember, I'm trying to give you the skills to do this quickly, not spend a lot of time. So I know I can write this out dimensionally, and it'll be very pretty, but I'm going to go, you know, and try to maximize your time and be efficient. So 0.1 molarity, and how much did I have to add? I had to add, okay, I'm not sure what this is here, but 14 milliliters, which has to go to liters, 0.014 liters. Molarity times liters. So I multiply that through, and I can do this. And what I get, party people, is I get 0.0014 moles. Moles of what? Hydroxide ions. All right, here's going to be a point on an AP when you do this type of math, or this kind of calculation where you're solving for what was the actual concentration of the acid in here. What do we know? Well, this has to equal what? 0.0014 what? Moles of H+. Hey, that's what the equivalence point is telling me. All right, so what do we do at this point? At this point, what we're going to do is take our moles and we're going to divide it by how many milliliters of what? In this case, liters of solution do I have here? Okay, people said, well, wait a minute, you added 14. Yes, we found out how many milliliters, here's my burette here, how many milliliters we used to neutralize that by using our pH probe. We could do with indicators as well, okay, but the point is, this is how much of the base was added. Yes, I know that we've added some, but we're trying to find the initial concentration. So we know initially from this titration, okay, that we have this many moles. Great. Let's find the concentration, okay, because that's part of the first skill here, is try to get, the whole point of a titration is to get some information about somebody you don't know. We have a standard solution of 0.1 molar solution base. It was standardized, and now divided by KHP, if you remember that, and now we're going to drop these drops of Jupiter here, these hydroxides, and we're going to stop it, or at least we're going to measure from our curve how much we have to add. We're going to relate that stoichiometrically, and we get moles. Let's get molarity. It's 25 milliliters. I'm telling you that in my beaker, but it's 0.025 what? Liters. Okay, so if we do this, and I'm just making sure I have this, I do 0.0014, and that's moles, divide by 0.025 liters. And what I get is 0.056. So what does this tell me? This tells me that I have 0.056 molarity, okay, of my original acid. And again, people get confused about what volume am I using. I'm using the volume in my beaker because I'm using 0.1, okay? What is the original volume? Yes, I had to add base to do that, but I'm going to go back knowing that it took that many moles of hydroxide, which is equal to that 1-to-1 stoichiometrically driven, right? that now I'm going to use the volume of the original solution. So knowing that you're on 0.1, okay, and you're solving for how many H pluses are on 0.1, you know you needed 0.025 liters to solve for the original starting point concentration of the acid, and that's another skill, okay? So that would be here. So if I was asking you to do this lab, number one, I forgot what numbers these are, but I want to see a what? Overall net ion equation. You should be able to figure out the solution concentration of the acid. It could be a base if we're switching this up here, but in this example, we're finding the concentration. Okay, good. And 4 helped us do that. But we still really haven't verified 0.1, 2, 3, 4, or 5. We just kind of used 0.4 to start the discussion. Now let's go back to verify 0.1. We have the initial concentration of the acid. This is it right here. But I want to verify the initial pH. With what volume? That's right, 25 milliliters in my beaker. I want to know what the pH is. Now, if this was a strong acid, first of all, the original pH should be lower. And if you remember the last titration we did, we had the same exact concentration. That's right. If you look at your graph, the other graph from the other lecture, or the other graph that I posted with this video, we started somewhere down here. It was 1.25 and it stayed low. And then it had a bigger asymptote. This in red is all new. That's all new. The concentration was exact, I'm sorry, this line intersected this 14 right in the middle. So they both, the acetic acid and the strong acid, hydrochloric acid, the both curves I'm showing you, had exactly the same concentration. Okay, but one is a weak acid. How can that be? How can that be? All right. So we made the same concentration, but the what? What's different is initial pH. All right, the pH was 1.25 in the last lecture. Here it's a little higher. Let's go find that. Well, it's very simple, okay? Now that I have the what? Now that I have the molarity of my acid and realizing it's weak, what I have to do now is I have to what? Use an equilibrium problem, okay? An equilibrium problem. So let's do that, okay? Let's kind of erase this. I know it's 0.056 molar for the acetic acid. That's the concentration. So let's get that off. I'm going to leave the moles. I'm going to leave that up there, okay? And let's do the equilibrium problem, because now I want to solve for the actual pH. Now what's pH? It's the negative log of the H plus ion concentration, which will not equal 0.056. This barely goes forward. Now, let me help you because it does get confusing. This is the reaction when we're driving it up the hill here, when we're forcing this acid to be titrated and forced forward. This hydroxide is forcing it forward. Okay, in this point we haven't added any acid. We've got a beaker sitting here. And so what's the reaction? The reaction's different. Let's write it. We have our acetic acid, H2, C2, H3O2, plus not the hydroxide. It's sitting in water. It's an aqueous solution. And in water, what's happening? We're in equilibrium. And so this barely goes forward, but it does. It becomes H3O plus. It's going to give a what? An H to the waters. And of course, it becomes the conjugate base. C2H3O2. And now that's negative. Notice the charge on one side equals the charge of the other. And this will go in equilibrium. Okay, and this would represent a Ka. Now here's our problem. I want this concentration. It won't be this. We need an equilibrium table. We're going to use the Ka of acetic acid to what? Find what value the H3 plus is. So what we do in equilibrium with our ice table, we're going to say that we have initially 0.056. Now some people don't like this because they say, wait a minute, I know it dissociates. We're going to assume that it's all starting undissociated, and then when we drop it in water, it's going to give up. And we're also going to say, well, this is going to go back some, but we know how much forward it goes based upon its Ka. So this is going to be 0. This is going to be 0. We don't do water. It's a liquid. Okay? It doesn't have a molarity. We know this is going to go forward somewhat, minus x, plus x, and this is interesting. In acid and bases, it's always 1-to-1. We always do an equilibrium table just for one proton changing. And of course, this is going to be 0.056 minus x. and this is X and X. So when I do the formula, and I'll do this up here, the Ka, hey, in equilibrium, what's Ka? Okay, the Ka is equal to what? Products over reactants. Hey, this is C2H3O2 negative. All right, now this is water liquid, okay? And of course, I'm sorry, we have this reaction here. We're sitting in water, and then we have what? H3O plus. And this is over what? Remember, this is an aqueous solution. So again, we have this reaction, so this water we don't count. I keep jumping around, sorry. H2, C2, H3, O2. Okay, well, party people, that's what the Ka is equal to. Now, look at the values. Well, you're going to have an X and X over 0.05 minus X equals the Ka, so let's write that. So it's going to be X times X, or X squared, all over. The value of my acetic acid is 0.056 minus X, and that equals the Ka. Well, we know that we have to look up or find the Ka, and that's a problem. We don't have the Ka either. Oh my gosh, but let's just think about this for a second. With this X here, we're going to have a quadratic happening. So what we do is we approximate away this X, not because we want to, because we can. Because the Ka is so small for weak acids, this value that we go forward is so small compared to this big value, it's insignificant. Okay, so we get rid of what I call the quadratic catastrophe in these types of problems. So we have this value. But our problem to solve for this, which is X squared over 0.056 equals some number, we need the Ka. Now we could go look it up and cheat a little bit, but we do not have to. Why not? Because we have an ability to solve for it. So before I can finish solving point number 1 or verifying its pH, I have to talk about some piece of information I know about point 2. Okay? So stay with me. A lot going on here. All right? So what do we know about point 2? Point 2 is called a halfway equivalence point. I like to call it the max buffer position, but we didn't have this in the last graph with a strong acid, strong base. Remember, it was a straight line. There was no buffer being made. Now, again, we haven't quite talked about it, but we'll get there. So what's so important about point 2? Now, if this is 14 milliliters, okay, then the halfway equivalence will be 7. So in my graph, I've got about 40, 20. So it's about, I was about right. So the halfway volume, I'm using the time here, the flow rate, no worries. If this is 14, this would be 7 milliliters. If it took 14 milliliters to completely what? Titrate and neutralize a strong base at half as much as 7. So this is the halfway point. It's the half-driven point, okay? So, gosh darn it, I can't answer this question until I get a Ka, but I can get a Ka from this chart, okay? And it's another skill. So besides doing the net ion equation, besides solving for the initial concentration, and now besides trying to verify these points, I can also solve for the Ka of the acid, which shows me how much forward or backwards it goes. Stay with me. Now, there's something special, okay, about this point right here. And if we haven't seen this before, I'm going to do a quick derivation. What do we know about Ka? Let's just do a simple Ha is an acid. It becomes H plus, and it becomes A negative, okay? Now, what do we know about that? Okay, well, this is the acid. Here's its conjugate base, and here's the proton. What's the Ka equal to? The Ka is equal to what? The concentration of the products to their stoichiometric coefficients over the reactants. The reactant is Ha, it is aqueous, it's not a liquid, and there we go. So what am I going to do with that? Well, party people, let's express it in terms of what? Negative log, because what is the pH? The negative log. So I'm going to do negative log of both sides. And so when I do the negative log of Ka, little p means negative log, I've got pKa. Cool beans. So pKa equals, now I'm going to split this up. I'm going to split this right here up, and I'm going to do the negative log of the H plus. Why? Because the negative log of the H plus is the pH, party people. And what else am I going to do? Then I'm going to do the negative log of the conjugate base over the conjugate acid. Ha! All right? Now, so what we have here is pK equals pH minus the log of A negative. Now, why do I care about that? Well, something's very interesting. Okay? Now, let's solve for pH. Okay? Now, I'm just going to kind of write this up here because it's that important. I know what the equivalence point is, and we'll write it again when we need to. But this is really important so you can see this. So what do we have here? I got pK equals pH. Now I'm going to solve for pH. So pH is equal to the pKa, and now I'm going to plus, right? So if I'm solving for this, it'll be plus the log on both sides. So pK plus the log of A negative over Ha, which is my acid. So what this means is pH equals the pK plus the log of the conjugate base over the conjugate acid. These, of course, is brackets, so it's concentration. So it's the molarity. Now, why do I care here? Well, this is the most important thing. So this is called the Henderson Hasselbalch, and it becomes unbelievably powerful here. So we've got this derivation. We've got the formula. Let me just get rid of this for a second. All right. Now, what's so important about this? Well, if I'm at the halfway equivalence point, okay? Think with me for a second. I've added enough hydroxide to half titrate, to half drive the reaction. Remember, it's stoichiometric. It's not going to do it by itself. So let's make up some numbers. If this is my HA going to H plus and the conjugate base, just making things simplified so we can study it. And if I do a simple ice table, okay, initially I'm going to have, let's make it 1 mole, because we're going to do stoichiometry right here. Here's 1 mole, and here's 0. Okay, now, when I add, bad Grotsky, because it's not going to do it by itself, right? So I'm going to need something to pull it forward. So I have my strong acid, weak acid, that's what we're doing here, plus the hydroxide is going to give me what? It's going to give me a smaller arrow so it fits on here. Equals what? Equals going to be A negative, conjugate base, plus water. Okay, water liquid. So when I do my stoich table, okay, mole, if I had 1 mole, I know I have 0.0014, and if you want to use those numbers, we can, but let's just do it with 1 mole, okay? So if I got 1 mole of this, all right, and let's say I half titrated. If I had 1 mole of that weak acid, well, party people, all right, if I'm going to half titrate, that means I have 0.5 mole. I have half the number of hydroxides to do that. That's what gets me here. Now, let's just start it this way. Initially, we have this. This is 0. We're not going to do the water because we can't measure its concentration. So that's initial. That's your initial. The change is what? Well, this is going to be minus something. Now, what's that minus? Well, if it's a 1-to-1 relationship and you have half as much, you're going to use up 0.5. The limiting reagent is hydroxide, so it's minus 0.5 because at the end, you're going to have what? 0. This is minus 0.5, minus 0.5. This is what? Plus 0.5. When you add that to 0, put that in your calculator, you're going to get 0.5. And lo and behold, if I drive this forward, what? Halfway, every single time, I'm going to have the same amount of conjugate acid as conjugate base. That's what's special. If I halfway titrate, I have half the amount. Why is that important? I don't care what the numbers are. If this number is the same as this number, and that occurs if I half titrate it in this scenario, the log of 1 becomes 0. And guess what? The pH equals the pKa. And so, party people, to finish the first question, I needed to start looking at the second, all right? And I needed the Ka. So if I carefully take a ruler, okay, or, you know, I could probably do this a more accurate way, but I'm going to say this is 4.4. I'm going to say the pH, it's about 4.5. Okay, this is 4.5. That's the pH here. At 7. Why do I know it's 7? It's half 14. Why I know 14? Because I found that from the equivalence. I know a lot going on here. But any case, what I have here is 4.5. And so, party people, when I'm at this point, this goes to 0 and pH equals pKa. And what do I have here? I have a value of what? 4.5. That's my pH, or my what? My pKa. Now, one of your skills that you must have to do these more complex problems, how do I go from a negative log to an actual number? In this case, a pKa, all right? This is really 1 times 10 to the 4.5, if you want to think about it that way, or 1 times 10 to the negative 4.5. So to go from in this case, a pKa back to a number, remember, negative log takes the number and makes it into an exponent. When you're already in a p format, you're in an exponent already. So because it's base 10, what we do is 10 to the negative x. Find your log key, and what I'm going to do is go second function, 10 to the x. Now it's negative log to become this. To go back, it's 10 to the negative x. So I go 10 to the negative 4.5. And what I get is I get 3.2 times 10 to the negative 5. Party people, by taking the what? 10 to the negative 4.5, I just found and converted that exponent into the actual number, and that number is 3.2 times 10 to the negative, my short-term memory is gone at this height, negative 5. Party people, that's my Ka. I was able to use that point. Cool. There's something else besides doing what? The net ion equation. Besides finding the initial concentration using the equivalence point, I now can find what? The Ka of the acid. Okay? By doing pH equals pK. Pretty important. But now I can finish point 1. Woo! Because now I got this what? Equilibrium of how much farther does this go forward. Not all of this becomes H pluses or H3O pluses. They're synonymous. So now I have my Ka, party people. Let's plug in. 3.2 times 10 to the negative 5. Okay, we're going to consolidate x and x. That's x squared. So we've got this scenario going. So let's solve for x. Okay, so what I'm going to do is times this number right here, the Ka. I'm going to times it by 0.056. And what I get is 1.77 times 10 to the negative 6. But it's equal to x squared, so I'm going to square root both sides. You should have no problem with this math at this point of this course. And when I do that, I get second answer. And I think I get 0.0013. It's carry 2 significant. So when I solve for x, I get 0.00, let's do 13. What did I just solve for? A, equilibrium. I solved for x. Well, who's x? The conjugate base. That's a negative there. And what I'm really after is the pH. That was the point. Okay, that's a point there, but that's the point I'm trying to make here. I think I made the point, but the point I want to really make is what is this pH? All right, so I've got the H3O plus concentration. To get the pH, hey, we negative log. It's the opposite of going 10 to the negative x. So I take my 0.0013 and I do negative log. I'm going to do second answer, close my parentheses, and I get a pH of 2.87, 2.9. All right, so this is 1, 2, 2.9, and so we're supposed to be here, okay? But it's still a good validation, okay? So, in any case, 2.9. All right, and now, we just validated that point, okay? We kind of used point 2 to what? Find the Ka. That's really what point 2 is really about, because at this point, the pH equals the pKa. So that's how we use point 2 to find the Ka. And if you need to find point 2, remember the volume of the titrate you're added is always half the equivalence. And that pH equals the pK. Now what if I gave you the Ka of the acid in a problem, right? And you didn't know the equivalence point? Well, you can do what? Take your Ka, do negative log, there's your what? pKa, and then you have that position there. Okay, so again, it can go backwards and forwards. All right, so cool. We're going to skip 3, okay, toward the end, because that could be anywhere. Now we're going to go to 4. We're going to find number 4. We're skipping 3. I'm going to make 3 somewhere in here, but I'm going to go to number 4. Now, you said, well, wait, didn't we work with 4 already? No, we sort of did. Okay, now let's kind of play this out, okay, as we talk about this. Now, 4 is important because 4 is going to be the place where, okay, we're making some buffers, and it's really important to see this point. As we go, we're going to hit that asymptote. Now notice in this curve compared to the other one, this kind of balloons up. Remember, the strong acid didn't, because this is what this point is going to show us. We hit this asymptote much, much later than a strong acid of the same concentration. But just like your other what? Titration curve, that middle of the asymptote is going to give us the same volume. I made this weak acid the same concentration. How can it be that the same concentration of a weak acid gives me the same volume of base added as the same concentration of a strong acid? Because the concentration that we have here is of this guy, and this guy can pull this one off and make it act as a strong acid in terms of its stoichiometry. Okay, so we found that. So let's go to 4. Now there's something very important in 4, as I'm trying to lead you there, is that we're going to validate its pH. Now unlike strong acid, strong base, 0.056, I'm going to write some numbers here so I don't forget. 0.056 is initial concentration, and that the Ka is 3.2 times 10 to the negative 5. And that just makes sure I remember. Okay, so here we go. Now, I'm going to validate this point. Now, if you notice, okay, we already had 2 different chemical reactions occurring. So this is 0.4. Now, let me step back for a second. Unlike strong acid, strong base, number 4, the equivalence point, was at a pH of 7. Now, this is 1, 2, 3, 4, 5, 6, 7, 8. It's 8 point something. What I'm getting, the pH at this equivalence point is like 8.6 or something. Kind of crazy. How can you be above 7 if we've neutralized? Remember, the equivalence point is where what? All of the hydroxides that were added equal the moles of the H plus in the beaker. Well, if it's completely neutralized, why is the pH above 7? Remember, most titrations are weak acid, strong base, strong acid, weak base. We don't do strong versus strong. Most of our tests are with weak acids, pharmaceuticals, weak acid, organic acids, weak. Things that we care about are weak acids, okay? So they're not gonna give us equivalence points at 7. Get that in your head, and the what? Net ion reactions will not be H plus hydroxide equals water. Bet your pony, okay, that you're gonna write that, or some people are. So I wanna be able to validate that, so let's do that, okay? So what happens at this point? And you should understand, at this point, we have 100% HA. That's your conjugate acid. At this point, you should understand there's what? 50% HA and 50% A negative, the conjugate base. Right? We half titrate. That's why the Ka equals the pKa. And party people, this is where we have 100% conjugate base. We'll make that A negative. And 0% theoretically, okay, HA, the acid. That's how it happens, okay? Now, what's the reaction here? Once I drive this reaction completely forward, match hydroxides, there's no more hydroxides, right? I drove it completely forward, right? In case of this, if I added 1 mole of this would be what? Minus 1 mole, minus 1 mole. This would be 0, and this would be plus 1 mole, and you'd have 1 mole. As many what? HAs as you have is how many conjugate base you make. So if we drive this forward, as many what? Moles of acid you have moles of conjugate base. So what we have now, party people, is a new reaction, okay? And now it's the third of these reactions. I know it gets confusing. The first reaction right here is the driven port, right to 0.4. So from 0, just after 0 to right to 0.4, that's the top. Then we get a different reaction of what? The acid sitting in the beaker. That was this plus water. Gives me the conjugate base, okay? But now, after I drive it forward, there is no more hydroxide. There is no more conjugate base. So what we have is there's no more conjugate acid. There's no more hydroxide. We have 100% conjugate base. Let's write that. So we have C2H3O2, negative. It's sitting in water. So we write it in water. Kind of like what? This sitting in water, okay? And what's the conjugate base going to do? It's going to pull an H. Bronston-Lowry bases pull an H. So what you're going to make is C2H3, remember this is negative, okay, and it's going to reform a little bit of the conjugate acid. And by pulling an H off the water, or as I like to say, ionizing water, okay, it becomes OH minus. Hey, you're going to produce some hydroxide. Now, in truth, were we making conjugate base everywhere? As we were driving this reaction till we ran out of both, at this point, we were making this along the way. Did it wait till the end? No. This was reacting with water going in the reverse to produce some hydroxides along the way. How do I know? Look how this balloons up. This starts at a higher pH because it doesn't dissociate, so it's what? Its acidity is less, so its pH is higher because it doesn't dissociate. It's a weak acid. But as we added base, we were producing another base that was ionizing water. That's why this is coming up and not staying as flat as the first one we just saw. So in this reaction, we're going to measure exactly how much hydroxide is being produced. And this is an equilibrium problem, not a driven problem. When we were in this position and we had the weak acid sitting in a beaker, that was what? That was, my friends, a problem, it was a problem of equilibrium. I'm checking the clock and I'm realizing, well, this is getting too long, but who cares? Having too much fun. So this was a position of equilibrium, okay? This one was not. This is essentially driving it forward at that position. When we get to this point, we have an equilibrium. So we're going to have to figure out our equilibrium pHs here. All right, so any case, how much conjugate base do we have? How much conjugate acid did we start with? Exactly the same amount. Whatever we had, okay, remember, we minused it away to go forward, to be driven forward. Now remember, this is an equilibrium table. It's not a stoich table. This is based upon molarity. So, party people, I write the molarity. And I wrote down 0.056. We found that as our first skill, right? 2 hours ago. So this is initial, 0.056. All right? Well, water we can't measure. Initially, we're going to assume that it all weighted to this point. I know it doesn't, okay? But we can do that. And there's 0, all right? And we have 0 hydroxide. And then at the change it's going to be what? Minus X as it goes forward a little bit. Remember, we have 100% conjugate base. It's going to sit in water. It's going to do its thing a little bit, okay? So it's going to lose some. This is going to be plus X plus X. Notice the X's are the same. For one of these, we'll produce 1 hydroxide and 1 conjugate acid. Okay, so at the end of equilibrium, or at equilibrium, we're going to have 0.056 minus X, and of course X and X. All right, well, here's our issue. This is a base reaction. This is the opposite of this reaction here, okay? So this is the acid dissociating, being forced to dissociate, okay? Or I should really say, when I had the acid sitting in water, okay, and it barely went forward based upon its Ka. Well, we have the conjugate base sitting in water. It's based on its Kb. So what is another skill we need? From a previous lecture, I taught you that Ka times Kb equals Kw. Okay, so what do we know? Kw is 10 to the negative 14. What else do we know? We know that 10 to the negative 14, we're going to solve for Kb, so the Ka goes in the bottom. Well, we know the Ka. 3.2 times 10 to the negative 5. So put that in our calculators and let's go find that. So we go second function, and we go e to the negative 14, divide by 3.2, second function, e, I don't like the caret key, negative 5. And what I get is let's make it 3.1 times 10 to the negative 10. So I found the Ka to be 3.1 times 10 to the negative 10. That's my Kb. Okay, no, it's as high as the Ka is, as low as the Kb. It's an inverse relationship. Okay, so let's get rid of that. We have the Kb because this is a what? A base dissociating in water. So how do I solve for this? Gosh darn it, the Kb is very simple. We're going to have these two. Aren't these guys x? So it's going to be x squared. I can do this. This is dead. Bye-bye. Okay, So we have x squared all over the concentration of, remember the liquids don't matter, right? So x squared, products over reactants. Hey, what's that concentration? 0.056 minus x. We approximate that away because base 0.056 is huge compared to 3.1 times 10 to the negative 10. So they can do that. And that's going to equal my 3.1 times 10 to the negative 10. Very simple, party people. Now let's solve for it. So all we got to do here is times the KB times 0.056. Okay, and then we're going to take the square root of that result. I get 1.75 times 10 to the negative 2. Square root both sides. X is equal to, the math you should understand. Second answer. Good Christmas. And what I get is my x that I just solved for is 4.18 times 10 to the negative 6. Now what's my x? Hey, it's either the conjugate acid or the base, the hydroxide. That's what I'm after. I'm after the pH. So what do I know? If I know my hydroxide concentration is this, and I want a pH, I'm going to get the POH. Okay? What's the POH? The negative log of the hydroxide concentration. So I'm going to take the POH. Okay? And so for me, I'm going to do negative log, second answer. And I get 5.37. That's the POH. 5.37. But I want the pH. What do we want? What do we know? 14 minus the POH gives me the pH. Okay, so you subtract that, or at least that from 14, and you get 8.62. All right, so again, these are skills we've gone over. pH plus POH is 14. pH plus POH equals pKw, 14. So 14 minus this gives me the pH, and I just found the pH by doing 14 minus this to be 8.62. And doesn't that validate this pretty well? I'm a little bit higher. I said 8.6, and I didn't know actually. Dead on. Okay, so pretty good validation there. But we had to realize what? That this was 100% conjugate base driven forward. It's going back a little bit. All right, and yeah, is some of this dissociating? Sure, but a small in comparison. Okay, and so we just validated that point. All right, let's do point number 5. That's a one that's the same as the one we did earlier in the year and the same as the one acid and base. This has no equilibrium. No equilibrium. So take a break from equilibrium. What do we know about the final pH? Well, party people, if this is my equivalence point and this is 14, let's go find the volume at the end. Okay, now of course I'm using silly flow rates here. So I'm going to do 100 divided by 2.8. And I get 35, let's go make that 36. So right here is 36 milliliters of what added on the bottom? Of the conjugate base, of the hydroxide in the burette. So, I know that I've added 14 to 36. Now the point I'm trying to make is here is how much base am I adding? At this point right here, we should know really well, this is pure water. And so the pH is just the extra hydroxides I've added from this point. So let's go find the concentration of the hydroxide that was added. Or at least the concentration of hydroxide at this point. Well, in order to get a concentration, which is a molarity, I need moles over liter. So let's get the moles first. Okay? Well, party people, what do we know? How much did we add? Well, 36 was added total, but from the 14. So I'm going to subtract. 6 minus 4 is what? 2. So 22 milliliters, okay, of base was added from the burette extra. Okay, we can do that. So 0.022 liters. Good, what do I know? Molarity times volume. What is the concentration of my base? I told you it was standardized at 0.1. Molarity times volume gives me moles. So I can do this without a calculator. I'm amazing. 0.0022 moles. That's how much moles of base I've added past the equivalence point. Okay? It's neutralized there, so we always go from that position. to find molarity, because I'm trying to find the pH, right? So I'm gonna get a POH and then subtract 14 minus that. Yeah, you see the flow, even though you're not here to say that, but hey, good job. All right, so let's find the moles. Now we divide by what? Well, let's understand, aren't we adding to a beaker? This is all happening with a pH probe sitting in this beaker. So I've added a total of 36 milliliters of base, okay? Whoa, just went dark. Okay, hold on. Okay, back in action. It's coming back on. All right, woo! Didn't pay the rates. Here we go. So, I just added what? I added 36 milliliters of base to a beaker that already had what? 25. So the total volume here is 36 plus 25, and what we get is 61 milliliters. You have to understand that if I'm finding the concentration of molarity, I gotta know the total volume added. I know it gets confusing. Here, initial pH, I'm in the beaker, okay? So here I'm saying I'm in the beaker and we've added all of this. So the total volume is 61 milliliters. I go to liters. Have to be for what? Molarity. And so now I'm gonna get this. So 0.0022, I'm gonna divide by 0.061, and what I'm gonna get now is 0.036. So the concentration is 0.036 molar for my hydroxide. In the beaker, after I added 36 to 25, what do I want? The pH. That's easy. Let's go find the negative log of this. It'll give me the POH. So negative log, second answer, negative log, I can do this, close my parentheses. I get 1.44. That's my POH. So my POH, and I don't have to write this, but I will, because POH is equal to 1.44. That's not your pH. 14 minus that. Okay? What you get is 12.6. So I'm getting the pH of 12.6. Now I don't know, this is 10, 11, 12. I'm getting 12 up here. Okay, it should be somewhere like right there, but hey, we're in the vicinity. So this point validating should be 12.6 pH. All right, good, we've done completely all the skills except for number 3. We found the what? We found the net ion, we found the concentration. We have identified all the points and how you attack this. Now we've got one more point, all right? So let's go after it, all right? And I'm gonna go after it the easiest way possible, and I'll show you the more difficult way, okay? Some other time possibly to save some time here, because we're going crazy. So how do I validate point 3? All right, so point 3, what do I have? All right, so let's make a point. All right, and I made a few today, I'm sure. So let's see, we said 14 was at equivalence point. All right, and let's go point 3 here. Now this is gonna be 30. That's my 30 seconds. Let's go find exactly how many milliliters that is. Divide by 2.8. Let's go find exactly what that is so I can see if I can validate my point. So 30 seconds, and again, you would be reading total volume here. 30 divide Christmas, so we gotta put those lights on. All right, lights keep flickering off because, all right, yeah, I'm still here, okay? Whoa, okay, whoa, okay. So now, they want to shut me down, but they can't. I'm continuing. 30 divided by 2.8. And what I get is 10.7, let's make it 11. So let's say 11 milliliters, okay, is this point here. So this was 14, we're gonna make this good old 11 milliliters. I'm sorry, a base added to the position. I want to validate this what? This pH at this position. Okay. Now, how do I do that? Okay, well, I'm going to go after the easiest way. When I'm in the buffer position, and what's the buffer position? The buffer position is anywhere just above 0 volume, just below that. This is the buffer position. I mean, I have conjugate acid and conjugate base. So think about this, I want to know how much conjugate base I have left, or how much I've made if I've titrated to this point. Remember, this is a driven reaction. We're going to drive it to the 11 milliliter mark. Okay? So we need a stoic table. Stoic table take moles. So what do we have? We have HC2H3O2 plus hydroxides, and we're going to make the conjugate base, same reaction above, and of course we're making water. Okay, what do we care about? Ice table. Now this again is not equilibrium table, it's a stoic table. Okay, now if you remember from the first point, probably 10 hours ago, the amount of moles that we started here was 0.0014. All right, that's how many moles we started in the beaker, okay? And we can rewind the tape to see how I got that. Now, if you don't like that, 0.056 and 25 milliliters, if you solve for it, make that in liters, you'd solve for that. Now, the question is, all right, I had that. Now, I had 0, and now I've got 0 of this. So I'm starting there. What I want to do is get to a position where I'm going to get to this position where I've added 11 milliliters. So let's go find 11 milliliters. 11 milliliters you know is 0.011 liters, and for the millionth time, take your liters, times it by the concentration of the hydroxide, you get moles. It's 0.10. So the molarity times the liters. So 0.1, right, times 0.1 gives me, it's a hard one, 0.001 moles of what? H plus were added at this position. Okay, so here's my stoic table. I have 0.001 moles. Okay, so what's going to happen? Who's the limiting reagent? It's a 1-to-1, so the little one is. This is minus 0.001. This is what? Plus 0.001. And this is what? Minus 0.001. Do the math. This becomes 0.0004. This goes to 0. It was limiting. Hey, look, we're right in 3. We're going to run out of hydroxide. We've got a lot more what? We need more volume of it. So it should make sense that I don't have enough hydroxide. And we made what? 0.001. Okay, party people. At this position, I'm in the same amount of solution, so I can do a little trick here. First trick is I can use Henderson Hasselbalch. And what do we know that we defined? pH equals what? pKa plus the what? The log of the conjugate base over the conjugate acid, HA. This is how you should go. We can do this equilibrium style and continue on with an ice table. I'll show you that tomorrow. But this is the way you want to do for speed purposes. Now, what I would do to put this in the concentration, because these are moles, I would have to what? Divide by the total volume of the solution, which would be 11 plus 25, convert that to liters. But because I'm putting them over each other, that volume is going to cancel. So I can put the moles over here. So look at here. I'm going to put in the top my conjugate base. And by the way, this Henderson Hasselbalch is given to you in your reference table. Yoo-hoo! Okay, so you got 0.001, I guess I'll call it coordinate, over my Ha, my HA, my conjugate acid, and that'll be 0.0004. Okay, so party people, let's do that. 0.001, again, you can spend more time and put them into molarities and then do them, but if you think about it, molarity over molarity, the liters of the same what? Volume will cancel themselves out. So 0.001 divide by 0.0004, and what you get is 2.5. So what's the log of 2.5? Okay, so let's do that. It's base 10 log, so log 2.5. And what I get is 0.397. That's what we have to add to our pKa. And I don't think I left my pKa up here, but I do have the Ka. So the pKa was, oh yeah, it was 4.5. So the 4.5 position is here. We have to add what? That little much. So 4.5 plus that. So 4.5, so add that to 4.5, and what you get is 4.89, we'll do 4.9. So the pH of that position is 4.9. And we just validated everything. And it's about right there, isn't it? Pretty close. Okay? Now, one last thing, and I will conclude, and I want you to watch. Does this make sense? There's a heck of a lot more conjugate base than conjugate acid. Why? Because we pushed it past. This is 50-50. So now we're going what? 40, 60, 30, okay, 70, 20, 80, right? So it makes sense that we have a lot more conjugate base. What is a conjugate base going to do? It's going to produce more hydroxides when it reacts with water. So it makes sense that we're adding. So that's why we're adding to this ratio, okay? What if I was in this position? Wouldn't this number be less than 1? If I had more conjugate acid in this position below the halfway point, this number would be what? Would be smaller than 1, which would make the make this what? Negative, and we would subtract from the pKa below. That's how the Henderson Hasselbalch comes to the rescue. Now I could answer this a whole different way. Okay, I could find the Ka, find how much we go forward, and we can solve for x and go through all of that too. So, any case, we're done here, and those are all the skills. A lot going on, but good luck.